In this video, we are going to go over clustering techniques using k-nearest neighbors clustering algorithm. So to start off, I am going to first create a new Jupyter Notebook file in our Colab environment. And I am going to call this file assignment 10 unsupervised learning. So just a brief introduction before we get in. So far, we've been doing supervised learning where we've had a target variable and we've been using a bunch of input variables or explanatory variables to try to create a model that can predict that certain target variable, and that's supervised learning. In these next couple of videos, we're going to be talking about unsupervised learning, where we don't really specifically have any target variable, but rather we are just going to give data to the algorithm and it is going to try to give meaning to that data for us. For this video, we're going over clustering, which is a way of how we are able to group observations together. So I'm going to first create a new section. I'm going to call this section imports, where we are going to import our data. I want to import pandas as PD. Let's import pandas. Let's also import Seaborn so we can get our data and display it, and also matplotlib just for some visualizations. So I'm going to import those. I have those imported. I'm going to create a new data frame, and then I'm going to have this data frame be loaded from data sets, and I want to use the iris data set. I'm going to load that data frame in. And now one thing I want to do before this, I'm going to use this data frame, is I want to give a name column or like an index column that that helps us know what observations are which points. If you already have a name column on your data set, you don't need to do this. In fact, this is not required at all for the analysis. Me adding this column. But the reason why I want to add a column called name is just so later we can kind of see when we display our data, we can see where different observations fall into our data. If you're using the MPG dataset, for instance, that already has a name column. So if you're following along with this assignment and you're doing your analysis on the MPG data, you already have a name column in the data set, so you do not have to worry about that at all. I'll show you this later on in the analysis, why I'm doing this though. But for right now, I'm just going to simply make I want my names to be flowers, and then I'm just going to give each flower a number. And the easiest way I can give each flower a number is I'm just going to reset the index, which will take this and make it a column. Let me show you what that does really quick. Right here. So that just makes a new column called index. Then I just want that index column, and right now it's an integer. I want to keep this, I'm joining this onto a string. So I want to use the as type function, and that will convert everything in this column now to strings. Okay, so now that I have that, I'm just going to concatenate that on. So I'm going to get flower plus whatever the index ID is. And now if I run that, you see we now have this name column where we have each of a number for each of the different flowers. That way, when we look at where an observation lands, we can then hover over it and we can see, oh, this is flower 0, this is flower 2, this is flower 147, so forth. And then what I want to do as well is I want to first pull up a pair plot, just so we can kind of get an idea of what this is going to look like. Actually, I'm not going to do hue. I'm just going to do a normal pair plot. And I'm going to talk you through what the algorithm is going to do. So you see we have this data, and what's going to happen is we are going to feed it this, we're going to run it through an algorithm. We're going to feed all this data through an algorithm, and then we're going to ask it to try to group the data. And so if we look at this pair plot and we try to we can get an intuition about some of the ways that this data might be grouped. And so let's say like we just want two groups. What will probably happen is this will be a group and this will be a group, or this will be a group and this will be a group, and so forth. And this will be a group and this will be a group. This will be grouped together and this will be grouped together. And that's what the algorithm is going to be doing under the hood. Now, if I add on species, you can kind of see that we do already have some natural groupings for this data. I'll give that a second to run. And so we do see, yes, this species, Setosis, falls into a separate group. And then we kind of have these two other groups for both versicolor and virginica for these groups. And you can also see that in just how the data is split up, especially here. When we look at petal width, we can really see the difference between the data. So it'll be interesting to see if our algorithm actually clusters the data like this. But now that we have our data imported, I'm going to add a new section called data cleaning. And I am going to do I'm first going to do df.drop NAs, and I'm going to get rid of all MAs. Then I'm going to drop columns, and those columns that I'm going to drop, I want to drop species, because this is too obvious of a grouping. If we put in species, it's too easy for the algorithm to group it. So we want to see how it does without species. Not because it's our target variable here, just because kind of the idea is we don't know what species is, and we want to see what groups it put things in. And just because species already gives the data a lot of structure, we want to take that out. And also, I would want to take out our name column that we created, because there's no point in having that column in either, since it's an index column. Also, if I want to, not that it will matter for this data set that I'm using, but if I do have any categorical variables, I can also use the getDummies function, and that will convert any categorical variables that I want to use into dummy variables. And the reason I need to do that is before I can feed any categorical variables in the algorithm, I'll need to first convert them to dummy variables. And I forgot to name this, but let's name this up here, df clean, and then df dummies. That looks great. And just for simplicity's sake, since everything's ready, I'm just going to call this df ready, make that equal to df dummies. Okay, and we should have our data frame ready to feed into our algorithm. So now I'm going to add a new section, and this is going to be our cluster analysis, or clustering analysis. So what I'll want to do is from scikit-learn, I'm going to import from clustering. I'm going to import k means. And then I'm also going to set our X matrix to df ready. And now that I have that, I can just go ahead and feed this into the algorithm. But one of the inputs that we'll have in our algorithm, and I'll show you what the algorithm will look like, our algorithm will look like, we'll call the k-means function. And something we have to do with k-means, primary input, is this n clusters. We have to choose how many clusters our data is going to have. So I know it's pretty obvious for this data set that it best splits up into 3 clusters just because there's 3 different species. However, I want to run you through some techniques and how to go about choosing the number of clusters, especially if you are working with a data set that you're not too familiar with. So I'm going to create a function here, or I'm going to create like a little for loop that's going to iterate through different possible clusters. And I'm going to call this sum of squared distances. And I'm just going to make a list. And the idea behind this is when we use the k-means function, we will deploy different centroids into into our algorithm. Actually, why don't I draw this out really quick? Let me bring something up. Okay, let's pretend that I have these data points right here. So what a k-means algorithm will do is it'll go on ahead and then it'll put some centroid here. And if we choose how many centroids we're deploying, and that determines the number of clusters. So if we put 1 centroid, what it wants to do is it wants to minimize the square distance. It's going to find a place to put this centroid that minimizes the square distance. So it might first start by putting the centroid here, but what happens is we have it's very close to this observation over here, but it's super far from this observation. So what it'll do is it'll redraw this centroid into another point over here. This is better, but then it'll finally converge it'll finally converge and have the centroid be right here so that it minimizes the distance. And then if you take all of these distances away from the different points, the distances from the centroid to all the different observations, and you square them, and then you get the sum of that, that gives you the sum of the squared distances. Now, if you have 1 centroid, it's going to be very high. However, if you have, let's say, 2 centroids, we'll put one like up here, over here, and one over here. Or here, let me change the color of that. Let's see. Colors will make this blue. If we have that just over here, oops, my pen's not working. There we go. If we have that over here, then we'll have these are all attached to this centroid over here, while all these other red ones will be attached to this centroid, and then they will essentially these will be in a group, and then these will be in a group. And the sum distances are going to be a lot smaller because there's more centroids. And the more and more clusters you have, the sum distances are going to go down and down. But to figure out what the ideal groups are going to be, we want to see when there's basically the biggest jump between where there's the biggest difference between sum distances and centroids. And that's going to give us an idea of when the best grouping happens. Let me go back. It's a little bit tricky to explain from this point, so I'm going to go back to the code, and it'll make some more sense in just a moment, but I'm going to just make a range, and I want to do a range from 2 to 15. And this can be any number. I can actually have this at 20 if I want to. The reason why I'm starting with 2, K represents the number of centroids or the number of clusters we're going to have. The reason why I'm starting at 2 and I'm not starting at 1 is because you normally ignore 1 because the jump from 1 to 2 will usually always be the highest, because of course if you just have one cluster, the sum of squared distances is going to be super large. So it's really hard to tell. It really doesn't matter having that in. So we just want to see everything from 2 clusters and up to see where the biggest differential is. So I'm going to create a for loop for k in this range of k's, and I am going to test out different k-means clusterings. And then I'll fit the model to our data that we're using by doing uppercase X, and then I want to get sum of our squared distances, and I'm going to append whatever our inertia, which gives me the mean of sum of squared distances. I'm going to run that, and that gives me my list of the sum of squared distances. I have this nice list right here. Let's clean it up a little bit and get into data frame. I'm going to call this elbow df, and I'll explain why I'm calling it elbow in just a moment. But let's put in, we'll put in the dictionary where k will simply be equal to k. Then we'll have the sum squared distances, which is going to equal the sum of squared distances. And then now that we have that, I then want to get the difference between each of the rows. So I'm going to make a new column called bend, and that is going to be equal to elbow SSD dot shift. So I am getting the value of the row above it, and I am subtracting it from the current value. And I'll show you what that looks like once we run this data frame. Okay, so now I have this data frame, and this shows me k, so the number of clusters. And when I have 2 clusters on the data, this is the sum of squared distances. Then when I have 3 clusters, this is the sum of squared distances. And then when I have 4, this is the sum of squared distances. And this number, this bend number, this is the difference between these 2 numbers here. And so you can see that what we're looking for is the point where this number is the greatest. So here we can see that it is the greatest at 3, meaning that 3 would be the optimal number of clusters to have. That's how we figure that out computationally. I also want to show you this in graph format. So I am going to create a plot in Matplot, and I'm going to call this K, and then I want to use, can just use elbow dot K, and then I can use elbow SSD, and then I'll make this BX. I'll add a X label as just K, and then I'll plot our Y label, and our Y label will equal sum of squared distances, and then I'll just say our title, I'll call this elbow method for optimal K, and then I'll show the plot. Okay, and if I run this, what I see is I see this plot, and what I'm looking for in this plot is wherever the elbow is. And the elbow is when we have a very drastic, let me draw out what an elbow would look like. It's where we would have a very drastic drop, and then we have like a less drastic drop, and then a less drastic and less drastic. So the elbow would be right here because this over here was the greatest difference between the two. So that's why this is called the elbow method, because we're looking at for where this point is. And in our case, this point is equal to 3 clusters. And we could see that by doing this analysis here. And also just to have an easy computational formula to figure this out. I can just use df.loc and then elbow df where bend is idx max. And that tells me where, and then I can just select the K column, and that tells me what our ideal number of clusters here is, which was what we were expecting given that this data set has 3 species in it. So I'm now going to use that for my number of clusters that I'll have. So I can go ahead and let me just set this to equal to my K, and I'm going to say cast this as an integer. And then I'm going to make the number of clusters that we have over here equal to K. And then I can fit that. Then I can fit, I can do a fit predict function. And what this is doing is it's going to classify I'm just going to classify all my X value or all my rows for me, and it's going to assign them a cluster. So I'll call that KMM, YKM. And then if I run it, now it's gone ahead and it's classified. It's given a number from 0 to 1, a classification for all of the different observations. So now that we have that, I want to go back. I want to make a new data frame called Canon model output, and that's going to equal our X matrix that we originally had. And I'm just going to copy that. Then I want to create a new column called assigned cluster, and you can call this whatever you want. Grouping is also another good name. I'm just calling this assigned cluster, so it's a little bit more specific. So what that does then is it gives each one of our observations or flowers a an assigned group. And because I want to do some stuff I want to play around with this more. I want to see. I'm going to add on. I'm going to add species back, which will be equal to our clean data frame. So let me add species, and then I also want to add name. Okay, and there we go. And then we can look and we can see we have our name column to identify in species. Now, one interesting exercise to do would actually be going through this and looking at how well it was able to, if the how well the classifications it has matches up with species. And you can see here that for Setosis, it's assigned everything to the same group, but for Virginica, you can see it's going back and forth between group 2 and group 1. And I want you guys to remember that this is an unsupervised learning problem, so we're not trying to predict species here. However, k-nearest neighbors can be used as a classification algorithm. You can use this there are classification algorithms. You can use this as a classification algorithm to try to predict species. And you can see how that can be possible here. Now, that's not what we're doing in this exercise. Rather, we just want to see how the data is best grouped, not necessarily predict which species they're in, but we just want to see how, given this data, it is grouped. And then a good way to visualize this is to I'll use our pair plots function. Model, oops, this model out, put, and then hue will be equal to assigned cluster, and I can run our pair plots. And you know what, while this one's loading, before I talk about this pair plots, I'm going to run another pair plots on species. Or there you go. Okay, so if we look at this, we can see a general sense of how it's trying to group all this data together. And you can see, so we have this data here, and then this data here, and then this data up here. So this right here, this is very clean, where we have almost little overlap between groups. And a lot of these are fairly separated. You do see, like in this graph, that there is quite a bit of overlap. But here we get not too much overlap. Here we get some overlap, but not too much. But you can see what the algorithm is trying to do is really go ahead and assign these groups. Now we compare that to, oh, what happened? Did I have assigned cluster? Let me just use our original data frame so we don't have to drop these other columns. Well, actually, some of those were interesting. Let me go back and use this. Before we look at that, I'll put these up side by side so it's a little bit easier to see. Okay, so here we go. We have our two different, this is species. This is how the species were already predetermined versus this is how the model ended up clustering them together. And so you can see they are fairly similar in how they did their groupings. One thing I do notice over here is this has a little bit more separation. Um, so the groups that the algorithm ended up choosing, see this? You can see there's a lot of overlap here and there's less overlap. The algorithm really tried to differentiate the groups more. However, the species itself has more overlap. So that's just something interesting to look at. Again, we're not trying to predict species here. We're trying to cluster the data into meaningful groups based off how different they are. But I do think this is interesting to look at how it's kind of like predetermined, how the predetermined groupings this data has versus how the algorithm went ahead and tried to group them. And now coming back down to this plot over here, you can see how um this is assigned groups. You can see how there is overlap with the assigned groups. Like ideally this would, if the groups were the same as species, this would be blue, this would be orange, and this would be green, but you are seeing some green dots here and some orange dots over here. And you do see that how there is a little bit of overlap on the green on the orange and a little bit of overlap on the orange on the green for these two clusters. So that's something interesting to look at. And what's so great about a pair plot is essentially you're getting different, almost like 3D rotations of the data. But there's only so much a 2D graph can show you. So what I want to do is I want to render this all out in 3D so we can better inspect the data. So in order to do that, I'm going to import Plotly, which is one of my favorite libraries for graphing. Um, just because how cool it is to make three-dimensional graphs. So I'm going to import Plotly Express as px. I'm going to make a figure. I'm going to make a figure equal to scatter. Scatter 3D. And then the data I want to use is going to be KNN model output. And then I'll simply just do the x as the x equal to sepal length. The y, I'll have it set to sepal width. And then the z, I'll set it equal to petal width. And I'll show you what that's done so far. So if we look at that, y is not a name. I spelled sepal incorrectly. Let me fix that. So there we go. So we have our basic. These are all of our different observations. That's only 4 of our variables though. So let me go ahead and add size as petal length. That way we can represent our 4 variables. So now we can see kind of, if we can see the different clusters here. And then what I can do is I can then go ahead and I want to get these colors based off of their assigned cluster. And I also want to give it symbols. And you don't necessarily need to do this, but I just want to see how it compares to species. So I'm just going to give it the symbols of square for one of the species, a circle for another species, and then an X for our final species. And then the symbols are going to be equal to species. And lastly, I want to give them hover names, and that's just going to be equal to the names we assign to it. But I run that, and so now we can see these colors represent the different clusters. So everything in yellow is cluster 2, everything in pink is cluster 1, and then everything in 0 is everything in purple is cluster 0. And then these X's represent Virginica, and these circles represent versicolor. And then these squares represent setosis. And so you can see kind of how the overlap that's here is the species is kind of in this circle where the color decided to, or the algorithm decided to split it here. And this is really interesting. And then like if I do something like this, where I just look at one side, we have sepal width here and then petal length. If I go up to our pair plot, what was this? Sepal width on the X, sepal length on the Y. See, sepal width on the X, sepal length on the Y. You see how we get our graph that looks like this, where we have blue going out this way, and then we have this other, or I guess the cluster we're looking at here is like this. So we should see one group here, and then a purple group here, and then the darker group up there. And I scroll back down, and you see, okay, that we see the inverse of that. I rotate this. There we go. Okay. So if like you look at that image right there and you put it side by side, you see where we have sepal length and sepal width, this is identical. And so this is why pair plots I think are really cool, is because you don't need to go ahead and do this 3D graph, because this shows you all the different rotations of the 3D graph. For instance, if we put petal, what is this? Petal length on the bottom and then petal width, we can rotate this. Actually, do I have petal width? Oh, I don't think I have that as one of my spatial axes. Let's see, what is this? Sepal width, sepal length, and petal width. Do we have that? Sepal length, petal width. There you go. Look at how that shapes. You have this cluster right here, and this cluster right here, and that cluster right there. But that is the introduction to clustering. That's a basic overview of what it does and just some interesting things to play around with. One of the things though that you'll notice is because we have so many different features, it's kind of hard to display or represent all these different groups, even with a 3D graph like this. And a 3D graph isn't necessarily something that you'd want to deliver, especially on a slide, just because it's so complicated. So what we're going to be looking at in the next video is something called dimension reduction, is how we can melt down these axes into and combine them together while still preserving the variance in the data in a way that we could actually display this in 2 dimensions. So we'll be going over that in the next video.